In the upcoming training minutes, we will now retrace step by step as to how the values of the individual variance components displayed in the output window came about, based on the 60 individual measurements. To get started, let us recall how these 60 individual values came about. 2 runs were defined here. In the first run, operator Zubak measured all 10 ball bearings. Then operator Gruska, followed by operator Stally. In the second run, operator Zubak again measured all 10 ball bearings again, followed by operator Gruska and operator Stally. So that each operator measured each of the 10 parts twice, resulting in our 60 individual values. Contrary to the ARM approach, where only mean values and ranges were calculated, and which were converted into corresponding standard deviations with the help of unclear adjustment factors from tables, we will now see that the ANOVA approach works completely without adjustment factors, and is also able to express interaction effects numerically. Therefore, the determination of the variation parameters with the ANOVA approach is also significantly more complex than the ARM approach. To determine the respective variance components based on ANOVA, we need some squared measurement distances for each source. These values then serve as a measure for the value of the respective source variation. These squared distances are called sum of squares in mathematics, and are marked with a double S and a corresponding lower footnote, from which it becomes clear which variation source is regarded. Basically, we are dealing with the following squared measurement distances, which are determined in the following order. 1. The sum of squares of the total mean, SS total mean. 2. The sum of squares of all measurements, SS total, abbreviated in the output window as sum of squares, that is sum of squares total, SS total. 3. The sum of squares of the operators, SS operator, abbreviated in the output window as sum of squares SS operator. 4. The sum of squares of the parts, SS part, abbreviated in the output window as sum of squares SS ball bearing. 5. In the fifth step, one of the important advantages of the ANOVA method compared to the ARM approach becomes apparent. Because in the fifth step, the sum of the two-way interaction, part-to-operator interaction, is determined. In the output window of our practical scenario, this is abbreviated with sum of squares, SS ball bearing, operator. This fifth step is a basic requirement to identify potential interaction effects that cannot be calculated using the ARM approach. 6. In the sixth step, the sum of squares repeatability, SS repeatability, is determined. In the output window, this is abbreviated as sum of squares repeatability, SS repeatability. And in the final step 7 to 10, the required number of respective degrees of freedom, listed in our output window in the column DF. With this information from these intermediate calculations, all standard deviations per source, as well as the standard deviation of the total variation, can be calculated. These standard deviations are then finally related to the standard deviation of the total variation, as in the ARM approach, and multiplied by 100%, so that a comparison can be made with the AIAG target specifications. Let us start with the calculation of the sum of squares of the overall mean. For this, all 60 individual values are first added up, resulting in a sum of 1262.95 millimeters. This sum is then squared and divided by the following product. Number of parts, in our case 10, multiplied by the number of operators, in our case 3, multiplied by the number of replicates, that is by the number of runs in our case 2. Which gives a sum of squares of the total mean of 26,583.6241. In the second step, we determine the sum of squares over all measurements. To do this, we first add up all 60 individual values squared, and subtract them from the sum of squares of the total mean, calculated in the first step, which results in a sum of squares over all measurements of 51.9117. We find this numeric value in the output window at this point. In the third step, the sum of squares over all three operators is determined by firstly adding up and squaring the respective 20 individual values for each operator. The three summed up and squared results per operator are added together and divided by the product of the number of parts and the number of replicates. And then subtracting from this result the sum of the squares of the total mean from step 1, which gives a sum of squares across all three operators of 0.0237. We find this numeric value in the output window at this point. In the fourth step, the sum of squares per part over all operators is determined. For this, all measurements per ball bearing are firstly added up and squared. Then all 10 summed up, and the squared results per ball bearing are added together, and the sum is divided by the product of the number of operators and the number of replicates, and subtract them from the sum of squares of the total mean, calculated in the first step, which yields a sum of squares per ball bearing, across all operators of 51.5789. We find this value in our output window at this point. In the fifth step, we determine the sum of squares of the parts operator interaction. For this, the measurements for each ball bearing and operator are added and squared. Then, these 30 summed up and squared results are added together, and the result is divided by the number of replicates. From this quotient, the following must then subtracted. The sum of squares per part, the sum of squares over all operators, as well as the sum of squares of the total mean, which gives a sum of squares of the part operator interaction of 0.1384. We find this value in our output window at this point. The ANOVA approach evaluates a possible interaction with this formula. The logic basic consideration here is that, if the 3 operator mean values over all 10 ball bearings are within the variation range of the reproducibility, there should also be a small variation within the 3 operator mean values per ball bearing. If, however, the 3 operator mean values, for example in the case of ball bearing number 10, are clearly different, then by definition we have an interaction effect here, in this case between operator Gruska and ball bearing number 10. Exactly this fact is checked with the already known hypothesis test. The null hypothesis states, at this point then, there are no significant differences in the variation behavior of the mean values. Respectively, the alternative hypothesis describes that in fact at least one operator mean value differs significantly and thus an interaction exists. In the sixth step, the sum of squares SS is determined, which results from the contribution of the repeatability. For this purpose, the sum of squares of the total mean from step 1 is subtracted from the sum of squares part operator and interaction part operator, resulting in a sum of squares of repeatability equal to 0.1707. We find this value in our output window at this point. In the seventh step, we determine the degrees of freedom for the source operators. With 3 operators, 3 degrees of freedom are available. And as we know by now, 1 degree of freedom is always bound by the respective arithmetic mean, so that the number of degrees of freedom for the source operator is 3 minus 1 equals 2. We find this value in the output window at this point. In step 8, the number of degrees of freedom for the source parts is determined. With 10 parts and 1 degree of freedom, which is bound by the mean value, the number of degrees of freedom for our ball bearings is 10 minus 1 equals 9. We find this value in the output window at this point. In the ninth step, we determine the number of degrees of freedom for the part operator interaction term. This is the product of the number of degrees of freedom for the part source multiplied by the number of degrees of freedom for the operator source, which gives a number of degrees of freedom for our interaction term 2 times 9 equals 18. We find this value in the output window at this point. In the 10th step, we calculate the still missing number of degrees of freedom for the source repeatability. This is given by the number of parts times the number of operators times the number of replicates minus 1. With 10 ball bearings, 3 operators and 2 replicates, this gives a number of degrees of freedom for the repeatability term of 30. We find this value in the output window at this point. With the results from these 10 steps, we can now determine the standard deviations that are important to us for repeatability, reproducibility for the entire measurement system, as well as for the process variation, that is the part-to-part variation. And on the basis of these standard deviations, the standard deviation of the total variation can be determined. The standard deviation of the repeatability is determined here according to the AIAG recommended formula. We had determined all the values required for this in steps 1 to 10. This results in a standard deviation for repeatability of 0.0802 mm. We find this value in the output window at this point. For the reproducibility, using the AIAG recommended formula, a standard deviation of 0.0165 mm is obtained. This value can be found in the output window at this point. The standard deviation of the measurement system variation in total results from the standard deviations of repeatability and reproducibility, which are firstly squared and added, as in the ARM approach. The square root of this result then gives a standard deviation for our measurement system in total of 0.0819 millimeters. We find this value in the output window at this point. For our part-to-part variation, that is for our process variation, according to the AIAG recommended following formula, and our determined results from the previous intermediate calculations, a standard deviation of 0.9768 millimeters, results. We find this value in the output window at this point. Therefore, with the help of the standard deviation of our measurement system, and the part-to-part variation, we now have all components available, in order to calculate the standard deviation of our total variation. This results in a standard deviation of 0.9802 millimeters, for the total variation of the measurements in our practical scenario. We find this value in the output window at this point. Finally, we have to relate the respective standard deviations to this total variation, and multiply it by 100%. This results in a percentage of study variation for the repeatability of 8.19%. We find this value in the output window at this point. For the reproducibility, the percentage of study variation, with regards to the total variation, is 1.68%. We find this value in the output window at this point. The percentage of study variation for our entire measurement system is 8.36%. We can find this value in the output window at this point. And the percentage study variation for the part-to-part variation is 99.65%. We find this value in the output window at this point. In the context of our gauge R&R study, now the percentage variation of our measurement system altogether with a value of 8.36% is relevant. This is because we have to compare this value with the target specifications of the AIAG. And as already discussed with the help of the automated calculations in the output window, the overall measurement system variation of 8.36% is below the 10% limit. And thus our measurement system can be used as an acceptable measurement system in the context of a process optimization. Therefore, we have also performed a full ANOVA manually, as part of a gauge R&R study for better traceability. This very extensive manual derivation of the variation parameters served exclusively as academic understanding. In day-to-day business, it is completely sufficient to perform the validation of the measurement system, on the basis of the results in the output window. Apart from the academic understanding, however, the extensive manual calculation also showed once again, how complex an implementation of the ANOVA method had been before the advent of computer technology. And it becomes understandable why the ARM approach, which is much easier to implement with paper and pencil, had its right to exist in earlier times. We had already discussed and derived in detail the information regarding the number of distinct categories displayed at the end of the gauge R&R section. With 16 unique distinct categories, it is above the AIAG minimum requirement of 5, so that in addition to a desirably low measurement system variation, there is also a desirably high measurement system resolution. The report on the gauge R&R study listed below, in which all important results are also summarized graphically once again, is both qualitatively and quantitatively identical to the report of the gauge R&R study, based on the average ranges method, ARM, and has already been discussed in detail in the corresponding training unit. The report of the gauge R&R study will also not be discussed again here. This is identical to the report based on the ARM method, and has already been discussed in detail there. Incidentally, the names of the three operators, Zubach, Gruska, and Stally, are an appreciative reference to the three responsible persons, Frederick Zubach, Gregory Gruska, and Stephen Stally, who together with other colleagues, made a significant contribution to the automotive industry, in the context of the preparation of the fourth edition of the AIAG Measurement Systems Analysis Standard. Finally, we save our study results as a project, by assigning the name, gauge R&R study crossed, under Save Project, in order to close our project, without data loss.